Okay, guys, how's everybody? The purple is our stereochemistry outline. But we need to finish up our reactions and alkenes. There's a few more. Okay, we're doing some reactions, and I think we can go back to the hydrants. Here, see how we did here? Okay, we have an alkene, we have chlorine and water. Chlorine and water, what's that going to form? A halohydrate. Okay, we're going to have an OH on one carbon and a Cl on the other. Which carbon is the Cl going to be on? Right. Well, we think mechanistically. What's the first intermediate? What's formed first in this reaction? Chloronium ion. I'm not going to show mechanism. We've already shown mechanism for forming that. You can think intermediates. Chloronium ion, right? Alkene reacts with chlorine, back bond. That's how we got to that point. All right, now we have water. Water attacks. Which carbon is it going to attack, left or right? Left. So these electrons make bond here. Something has to leave, so the chlorine, these electrons are kicked off. They move on to chlorine as a lone pair. We call the chlorine a leaving group from the tetrahedral carbon. It's the same old mechanism. And that will give, not a final product yet, that gives that intermediate. And then there's another chlorine here. This chlorine takes the H. These electrons stay behind. That's just an acid-base reaction. And we get the final product. Which looks like that, which is a halohydrate.
Could water also have probated?
I can't hear you.
Could water also have probated without the chlorine?
Water could have taken the H. Yeah. Because what else did we make here? HCl. How does HCl exist in water? HCl exists like this in water. Okay? So if you had used water to take the H, you would have formed that directly. It's the same thing. I like to reform specific things for a balanced line reaction. I will reform strong acids. Even though in water a strong acid is ionized, it's really H3O plus and whatever minus. Okay, one below. Well, that's one of the easiest reactions in organic chemistry. One carbon gets Br, one carbon gets Br, right? You don't have to decide which goes where. It's just adding Br2 across the pi bond. And these two reactions, we don't have any relative stereochemistry. This is chiral right there. You can look back later on. But there's really no stereochemical considerations for us at this point. That's just bromination of the pi bond. You should be doing that in lab pretty soon.
So the other carbons are chiral?
The carbons that I starred are chiral. It's a carbon with 4 different things attached. All right? All right, this alkene with ICL. We know ICL is polarized. So the double bond essentially attacks which halogen? I or the Cl? I, this is the one with the partial plus. Then the I back bonds, and so we get a what intermediate? Iodonium ion. And then the chlorine attacks the iodonium ion, but then which carbon does the chlorine attack? More substituted. So what's the product? But hold on. When you have a ring, you're going to have stereochemistry. All right? Let's just state that right here, because you don't have free rotation. Let's show the iodonium ion. It's a 3-membered ring. Both bonds have to be the same. Okay, I can't make a 3-membered ring. I want to make a 3-membered ring here. I can't have one bond going back. There's no way for these things to bond. It has to be the same side. I'm going to draw both of these bold. Okay, and I'm going to draw the ethyl dashed. Could have drawn it the other way. Now the chlorine attacks which carbon, top or bottom? Bottom. These electrons here push off the electrons of the leaving group. They move on to the iodine as the third lone pair. So what's the stereochemistry now? Iodine just opens up. It now has 3 lone pairs, because what does that arrow mean? These electrons moving on to iodine as the third lone pair. How's the chlorine? Dashed or bold? Chlorine is dashed. And the ethyl is bold. So the iodine is sitting like this, both bonds forward, off the board. If the iodine bond is forward, how does the chlorine come in? Behind the board, kicking off the iodine. But it just opens up, it's still attached to the other one. Iodine forward, ethyl back. But when the chlorine comes in, it pushes the ethyl forward. Okay? And there's only 3 lone pairs on chlorine, because the 4th lone pair is now a bonding pair. And so we added ICL across the pi bond, that's the terminology, but the I and the Cl are in what relative orientation? They're trans. We're not doing halohydrin, we're doing addition of X2, but they add anti or trans X2, or could be interhalogen, 2 different X's. Okay? Trans addition, coming from the backside attack. Below, DCl. This may be our first look at deuterium, which is an isotope of hydrogen. It just has 1 extra neutron, and so we call it D, but it reacts as if it's just H, okay? So really that's HCl, it's just a special type of H. And so we're adding HCl here. Is the H going to be on the top or bottom? Carbocation chemistry. What's the mechanism? Pi bond attacks H, leaving carbocation. Okay? Whenever an alkene attacks an H plus or a D plus, you get a carbocation. Alright, let's just call this D plus Cl minus. These electrons, like this, they hinge and go up and make a bond. Alright, these go up and make a bond. We end up with a bond to D, there's an ethyl, and there's a plus on the more substituted carbon. Is that really a carbocation, or should we say NAF?
Carbocation.
Why is it a carbocation?
Actually,
Why is it actually formed?
because the hydrogen can't form the ions, so it's not strong enough.
Because the deuterium does not have a lone pair. Does it have a lone pair? No. It cannot back bond. Whenever the alkene attacks H+, it's a true carbocation. Okay, let's review. Reactions with H+. All these react with H+, involve a carbocation intermediate. Okay, whenever you react with H+, it's a carbocation intermediate. These down here that we're doing, no carbocation intermediate. These are not H+. Everything else we react with is going to do some back bonding. But H+ or D+ cannot do back bonding. So it's a carbocation there. Chlorine attacks here. Next step is you got this and you got Cl minus. These electrons make bond, and you end up with deuterium and chlorine. See, that's 4 things bonded there. Here's your product. In terms of regiochemistry, D here, chlorine there. Question, is there relative stereochemistry between the D and the Cl? Is it particular? Is it trans? Is it cis? Is it both? Well, come back over here. What's the geometry of this carbocation? Trigonoplanar. What's the geometry of this carbon? It's tetrahedral. See, there's an H there. Now there's an H and a D. 2 in the plane, 1 forward, 1 back. Do you want to show this bold or dashed, Connor?
Bold.
Okay, we could have also showed it dashed. Okay, if that's bold, what's the chlorine down here?
Dash.
Why do you say it's dashed? How do you attack a carbocation?
Generally,
Head on this side.
closer to easy.
Either side. We've said that 5 times now. You attack 2 different places. If you attack a carbocation, it's either side, because it's planar. If you attack a carbon that has a leaving group on it, how do you attack it? Backside. How do you attack a carbocation? Either side. If it attacked from the front, you would get that. And if it attacked from the back, you would get that. So is the D and the Cl going to be cis or trans? Both. Random. You're also going to get enantiomer. That's going to give four stereoisomers. And once we cover stereochemistry, you can look back at that and see why it's 4 stereoisomers. Because up here, this could have also been dashed. So that's just an isotope of hydrogen. We call it D. Main reason it's used is because it allows for doing HCl, but having 2 different things. Now, H and D is different, so it allows for some stereochemistry. How do we do on those? I'm assuming you all did those over the weekend and then got some questions answered right now. Anybody have additional questions? Let's look at these here. I think we did the first one, yeah, in class. And we have a cyclohexene. What is this? Peroxy acid condensed. What does that do to an alkene? As I mentioned, with your predicted products, you got to have it ready to go. Okay, alkenes react with peroxy acids to give what? Oxide. Boom. There you go. And then there's mechanistic thought that goes with that. There's stereochemistry that goes with that. I mean, this is just going to replace the double bond with that, right? Okay? We've already done the mechanism. But let's look at that. Once it does that, don't we have stereochemistry? We do. These are both tetrahedral. So that means 2 in the plane, 1 forward, 1 back. We'll put the ring in the plane, 1 forward, 1 back. Now we can show this forward. If that's forward, how do you want to show the O bond? Let's show it back. Now if that's back, see this is also tetrahedral. 2 in the plane, 1 forward, 1 back. If that bond is dashed, how is this bond going to be? Brianna? Why does it have to be dashed? This is back.
Oh, no, it's an H coming out.
Why does that have to be dashed?
Because that one at the top is going to the back, going to the hall.
So why does that have to be dashed?
The ring has to be
Because the ring has to be the cis. If one bond's coming out and the other's going back, how are these bonded together? Remember, ring's got to be cis. Okay? They have to be both forward to bond. So the H here is us back. I'm not going to draw it in though, because it's an H. Okay? That's where the reagent was in the hull. The alkene attacked the oxygen back bonded, but all those bonds are back. But see, the reagent can also be over here, and everything can happen forward. But you can also get both of these forward and the methyl back. Basically, whenever you generate tetrahedral carbons, very often you need to show the tetrahedral nature. Primarily, and really only when it's chiral. We will define that later. Chiral is when there's 4 different things attached to the same carbon. There's 4 different things attached to this carbon. A methyl, an oxygen, this, and that. These are different because if you come this way, you hit an O bond. Again, 3/4 of this, you should know this point. The other little bit, you come back and review this after we cover stereochemistry. Okay, I'll do one of these here, because this is something I need to show you. All right, we're making an epoxide. that right there is the product if you just disregard stereochemistry. There's your connectivity, right? We turn the alkene into a three-member ring oxygen. What type of stereochemistry do you want to show here?
At least a 6 train.
Now you could show these bold, and that would probably work, perhaps. That's not the way I would do it or I would recommend it. Let me show you how I would do this so you get the stereochemistry correct every time. Would you like to see it how you, where you always get it right? Okay, let me show you how you do it. Now in a week from now, please remember this point right here. It's 20 after. I'll remind you of this. Many of you won't remember. All right? Please remember. Here we go. What I would recommend doing is turning this so instead of it being flat on the board, like this, see this is planar, it's flat, and this is as if it's flat on the board. Instead of that, let's turn it like this. Do that first. Now if we turn it like that, I'm still going to draw this like this. But these are trans. Now if I drew it like this, it'd be easier to see what I'm about to do. If I have that, here, let me draw it on the paper. Okay, there it is on the board, all right? Now, this is X and this is Y. See this X straight down? Now, when I turn the paper, I want you to tell me if X is forward or back. All right? See X? I'm going to turn it like this. Is X forward or back?
Forward.
It's now forward. All right? And the Y group is?
Back.
Okay? That's all we're doing. This is just turned a little bit instead of like this. Now, when I turn it, I can show this still like that, but I can show X like this and Y like that. All right? So that means I turn, now Y is going back, and I can draw it like that. Well, the same thing up here, except it's just a little bit, instead of horizontal, it's a little bit turned there. I'm going to lift it up a little bit. Boom. These groups are trans about the double bond. The methyl and the alkyl are trans. I'm going to draw this one. You can do it either way you want, as long as they're trans. I'm going to draw this one forward. And I'm going to draw this one like this. Okay? These are the same thing. I've just turned the alkene like that. Now, when you do the epoxide, what happens? We get rid of the double bond, and we connect the oxygens. We add in one oxygen, and it's like that. And I'm not going to redraw it, but there's your product. We turn the alkene. Now instead of a front and back, we have an up and down. This is where the reagent was at the up here. The pi bond attacked it, made the bond up, and then the oxygen back bonded. And we have two bonds straight up. But you could also have the reagent come from down here. Pi bond can attack the oxygen back bonds, and both bonds are down. You get both bonds down, you don't change anything. There's your starting alkene. Difference is you draw this down. And those are your two products.
Question, how come when we rotated it forward, so like the X group came forward and the Y group went
You
back?
could do either way.
You can do either way, so what would it look like? Would it be the same if you did it, if you rotated it the other way initially?
It would be the same. It would just not be drawn on the board the same.
Okay, how would that be, what would it look like if
If we had turned it the other way, we would have gotten, you want to draw this like this, and this like this
it was drawn? So we would do the same thing?
instead,
Yeah.
and then we could put the oxygen. Now these are not the same. These two are the same. You get the same outcome. Those two are the same though. Because from here, if you want to have it just like this, you have to flip this over. Ethyl coming out. All right? Ethyl coming out. That's what bold, coming out. But if you flip it over so the oxygen is down, now the ethyl's going back. Okay? You get the same two.
Okay.
We'll further define these. These are called what? These are enantiomers. We will define these in a little bit. But what I showed you here is how you get to enantiomers.
So what kind of mistakes could be made here if you were going to draw a planar ring anyway with starting with trans alkenes, basically just putting them.
The way I drew it first. The way I drew it first was I put the oxygen bonds dashed in bold. I see more potential for mistakes doing this. Do it like this. We really fix our stereochemistry before we do any reaction. We fix the stereochemistry just by doing this. And now you either have the two bonds straight up. That's straight up in the board, not forward or back. Or you have it straight down. And that's the way I'm recommending doing these. These that can rotate. When you have dual stereochemistry, relative, you end up with relative because there's your ring, but this methyl and that's trans. And then you say, well, why is that trans? The oxygen's straight up. Yeah, but the groups are trans. There they are. You do it like this, everything's right there. You describe it however you want. So your outcomes don't have to be memorized. Your outcomes come from your process, and then you say, well, it is trans. You don't memorize that. You just do it and then look at it. Do the one below on your own. What is MCPBA? Just a specific type of peroxy acid, right? Do that on your own. Let's see where we're at. Okay, epoxide. You finish those up. Is that where we ended last time? I think so, because I don't think we've done cyclopropane. Another three-membered ring, except here we're going to have all carbons. And so instead of an epoxide, it's going to be a cyclopropane. Three-carbon ring. We will see it's very analogous to bromonium ions, etc., epoxides, three-membered rings we're doing here. Lots of drugs actually have cyclopropane. And I'm kind of working on paper to sort of highlight that. That could be published in some type of medicinal journal or a chemical education journal. Maybe one day. You can find a good student who can write. Interested in doing that. Cyclopropanes. How do you make them? One way to make them is using simple CH2 carbene. What is a carbene? CH2. We draw a Lewis structure for CH2. How many valence electrons in CH2? 6. I'm thinking the C's in the middle and the H's on the periphery because H only makes one bond. Everybody with me? Here's 4. I got 2 more electrons. Well, H doesn't make double bond, so you're not going to put double bond. Where are you going to put the other 2 electrons? Not a lone pair on carbon. All right? Anybody see another structure we could show? Can we make more bonds? What else can we do here? CH2 is a known species. There's a structure. That's the only structure I know we can show. Does carbon have an octet? No octet. What's the charge of the carbon? It's neutral. This is an exception to, I said, if it's not typical bonding, it'll probably have a charge. Well, that's certainly not typical bonding for carbon, because that's not 4 bonds. Usually you want to find a charge. There's actually no charge, though. A carbene is a neutral carbon that has no octet. It's usually called divalent. Divalent means the number of bonds it makes. 2 bonds, divalent. Okay? It's sp2, it's trigonal planar. It's got 3 regions around it. Got an empty p orbital. Graph that. It's sp2. That means it's got 3 hybrids, right? P orbital left over. What type of bonds do you see? Bond to H, and then a lone pair. But it has an empty p orbital. I mean, it doesn't have an octet. It's missing an electron. And all these electrons are spread out trigonal planar. That's really not linear there. Okay? What's the bond angle to the HCH? It's really 120. Okay? All right. How do you make CH2 carbene? You can make it from what's called diazomethane. 1 carbon is methane, 2 nitrogens di. Azo means nitrogen. It's called diazomethane. It's a toxic gas. Here's the structure here. Lewis structure for diazomethane. And this Lewis structure, you can see how you get to this point. That's a minus, that's a plus. Net neutral. It's a neutral molecule. If you heat this, the nitrogen will just leave. Can an atom just up and leave? We've seen things come in and kick an atom off. Can atoms just up and leave? What happens when you put HCl in water? What happens? What does it do? Sophia?
Breaks the bond breaks, and they're separate.
You did this. Talk about the electrons or atoms.
Or what?
When you did this, are you referring to electrons or atoms?
The atom.
Atoms, yeah, but not electrons. How does this break? What do we call it when it breaks? What's an ionizes, right? You put this in water, what happens? Chlorine leaves, takes its electrons and becomes An H with no electrons, that's plus, Cl minus. Right? Ionization. What makes that do that?
Hydrogen bond.
Hydrogen bonding is something that's energetically favorable. Okay? Well, it's the same thing here. This is just open leaves. What makes this do this? A little heat. One molecule going to two. What's making that do that? Entropy. Entropy is increasing. And temperature magnifies what term? Entropy. So if you can add some temperature, it's going to make the entropy become even more influential. Yeah. If you heat this thing will ionize. Well, it's already an ion. You say, well, what does it mean ionize? Well, it's very similar to ionization, except we don't create new ions here, actually. We kind of do. We make this, well, charges are a little bit odd. If you heat diazomethane, it'll release nitrogen gas into gas, and then will form your carbene. Why do I have a plus and minus charge here? CH2 with a lone pair. CH2 with a lone pair. Because usually a lone pair is like a minus. And usually an empty orbital is like a plus. Okay? It's got dual character. Ultimately, this is neutral. But a lot of times people will show plus and minus to illustrate the dual character. But it's net neutral. Now once we have this portion here is called, what's a generic term for this in terms of its reactivity?
So electrophilic.
Is this electrophilic or nucleophilic?
Good.
Would this like electrons or would it like a positive charge?
Electrophilic.
You would love for electrons to come in here. This is your electrophilic portion, and in your lone pair is your nucleophilic portion. It's got dual character. The pi bond will be attracted to the empty orbital, or the positive portion. Let's go back and just very generically. Why is a pi bond attracted to H+? We said because these are electrons and that's positive. Okay? But where are these electrons adding to? H+. This has an empty orbital. What's the name of the orbital? S orbital. Okay? This has an empty S orbital. Well, this has an empty p orbital. And that's what these electrons are kind of pumping into. Now let's show that. If these electrons hinge up here, okay? Somebody grab my finger there and pull it up. That's what that arrow means. Okay? We're yanking it up. The electrons are moving up here to attack the carbon. And now we have this bond. And that's what we have. Let's forget about that arrow because that's moving here. Where are you going to make positive? Left or right? Left. So we hinge away, make positive. Now that has 3 bonds and a lone pair, but now that's a minus. Now what is this electron going to do? It's going to back bond. And when you back bond, what do you get? You're done. Well, that's a CH2, you just back bonded. You don't even have to remove an H. Is this actually formed? No, because anytime you can back bond, that's going to happen at the same exact time. Okay, heat it up, carbenes form, alkenes walking along, I see an empty p orbital. As soon as I attack the p orbital, you lone pair back bond. Here we go. Cyclopropane. Okay? Attack the orbital, you're back bonding this. As soon as I'm attacking, that's a transition state. Alright? You see the similarities of bromonium, epoxide, cyclopropane? We do have to form our reagent. You know how that's formed? Lewis structure for diazomethane. This is not convenient to do in lab, especially for beginning organic students, because this is a toxic explosive gas. If it gets out of the tank, it'll chase you down. Okay? Much more convenient to make these carbenes down here, one being the dichlorocarbene. Much more convenient here. This involves chloroform and hydroxide. Here's chloroform, carbon with 3 chlorines and an H. That H has some acidity. Hydroxide will act as a base, take the H. And of course, that's the same acid-base mechanism I showed you a week and a half ago that we will always do, right? Lone pair takes H, these electrons move on to carbon. Okay, what does this give? What are we forming there? Water. And what's happening here? Electrons are moving on to carbon as a lone pair. That's a minus charge. This minus is sort of similar to the minus of diazomethane, except this structure is a full minus. At this point, the chlorine will just leave. And when it leaves, you get a divalent carbon, a carbene. It's net neutral. We can show minus and plus charge, very similar to that up there, and Cl minus. This may require a little heat driven by entropy. Why would this chlorine leave? Because it's a nice guy. See, carbon is minus. And the chlorine's like, okay, carbon, I know you don't like being minus, so let's do this. What if I just leave and take electrons with me? I'll be minus. And you can be neutral. Because that's actually neutral. So chlorine's like, okay, you take a hike, and I'll just be neutral. It's like, well, I only have 2 bonds, but at least I'm neutral. Okay? But there is a carbene, it happens to be the dichlorocarbene. With the chlorines here, this can happen, because without the chlorines, this won't be acidic. So that helps this happen, you end up with that, but that's okay. Now we can attack back bond, and we get a cyclopropane, but it is going to have 2 chlorines on it. And that would be called a dichlorocyclopropane. But those are actually much easier to make because chloroform is a liquid, hydroxide is very common. So we can have reactions like this. The one above I want you to do on your own because it's very similar to when we rotate it. Okay, you see this alkene here? I'd recommend you rotate it first. And your bonds to the cyclopropane, are they going to be cis or trans? The bonds to your cyclopropane. It's got to be cis, right? I mean, it's walking down the road. Here's your alkene, it's planar. Bond to carbon and you back bond. Both bonds are going to be on the same side. Unless he's going to throw a curveball and bond over here. That'd be a long bond. Do that when you're on your own, rotate it. You got to know what your reagents give. Diazomethane gives cyclopropane. Let's do this one down here again. What does this give? What does this do to an alkene? Chloroform hydroxide.
Same thing.
Lower.
It's going to make a
Dichlorocarbene. Anytime you see chloroform hydroxide and an alkene, it's dichlorocarbene. You're not going to see chloroform used for much else in organic chemistry other than just being a solvent. In terms of a reagent, this is dichlorocarbene. There's your alkene, and so we have, in terms of connectivity, it's just that there. But show this with stereochemistry. because these two carbons are now tetrahedral, and they're actually also chiral. So show it with correct stereochemistry.
Would we assume that it's in water if it has like that written up, the KOH on the bottom?
Show what?
Are we assuming that's in water, or is that something you could, something you can make, or is it even necessary? To have the OHs? I guess I might have, we said written H2O on every other one of them, and now we just have heat, so I was just curious if it can be done not in water. If you get this hydroxide ion to react with the fluor.
Probably a little water there. I'm wondering why you asked.
Just because I thought we'd always written it before, so I didn't know if it was possible to do it.
But we didn't write it up there.
Okay.
Potassium hydroxide is not going to dissolve in chloroform. Probably going to have some water to get it dissolved. But then it's probably going to be two phases. So then you might include a phase transfer catalyst. Okay, we got product. Something like that. Everybody get something different? Yes, that would be the enantiomer. Once we cover enantiomers, you can look back and see that. There's lots of drugs with cyclopropane rings. This is just a little article about carbene that's actually formed during a metabolism of a drug. But we're ready to look at oxymercuration. Okay. Review. We take this alkene, react it with aqueous acid, that is water with an H plus catalyst. You get hydration, you get this product. We've already shown this product. That occurs because of a hydride shift. That's because you get a carbocation and then the H minus shifts over. You get a carbocation here and then water attacks. What if you wanted the OH here without a rearrangement? You'd have to do it by different reagents. That's going to rearrange. But if you do it with these reagents called oxymercuration, first mercury acetate with water, and then a second step, sodium borohydride, we can get this product, no rearrangement with the mercury ion. The reason we don't get mercury any rearrangement is because there's no carbocation formed. And so on our here, none of these have carbocation. We've made it to here. No carbocation. So how does this reaction take place? Well, we have to know a little bit about mercury acetate. This we can show, if you show it fully ionic, what's the charge of the mercury if it's fully ionic? I can't hear.
2+.
2 plus, because acetate is minus, and there's 2 acetates. Okay? But I'm going to just show it partially. Okay? We just ionize one of the acetates from the, it looks like formula, but if that's minus, here the mercury is just plus. This is just where one of the acetates ionized. We can show it in this form. Okay? But essentially we have an Hg plus. That means it's electrophilic. It's missing an electron. Hg plus is analogous to H plus. And the alkene will attack the Hg plus. Now when this attacks the Hg plus, are we going to leave plus on top or bottom? Bottom. So this hinges away, attacks the Hg, but it's actually over here. What does that give? Which bond is the mercury now? Which carbon is the mercury now bonded to? Top or bottom?
Top.
Top. Who said bottom? Nobody said bottom? I was wondering why he said bottom. Okay. On to the top. What's here? Carbocation. Okay? The basic alkene mechanism is the same over and over. If you learn it that way. Right? What have we done different? We just have to be shown that this is Hg plus. Alkenes attack it, the acetate's there, that's now neutral. Alright, now what's next? Well, mercury does have a lone pair. It actually has more than one. So that's important to know. Since it has a lone pair, what's it going to do at this point? Back bond. How'd y'all figure that out? Because that's what we've been doing, right? This is going to back bond. What does that give? Hg there, acetate there. I'm not going to show the bond, just as. Now, do you think this is actually formed? Or does, as soon as the alkene attacks the mercury, is the mercury back bonding at the same exact time? Same exact time. It's not actually formed. And your textbook probably won't show it. Now, this species positive, shouldn't this be positive? Because the charge changes disappear. What's positive now? It's actually the mercury, because the lone pair used to belong totally to mercury. So it got to count 2 electrons. But now the lone pair is bonded, it only gets to count 1, so it's 1 less electron in the count. So mercury is now positive again. And that positive mercury is analogous to what? Well, in the 3-membered ring. Bromonium ion. Or a protonated epoxide. It's a 3-membered ring with a, okay, it's analogous. The water now attacks, just like it attacks a bromonium ion. Which carbon is it going to attack, top or bottom? substituted. It's the same old thing, just as if it was a bromonium. Water attacks here, and the mercury leaves that carbon. What does that give? Gets its lone pair back with acetate, but now that's actually neutral. What's now bonded to this carbon? Water. So that's what attacked it. Now, watching all this was the acetate. This minus we'll take the H, these electrons stay behind, and you end up with that plus acetic acid. And this is end step 1.
So is water added separately? You first have to add mercury acetate and then add water, or they're solvents?
Now the water's there the whole time.
Okay.
The alkenes don't react with water. Skin of an apple is alkenes. Water doesn't affect the skin of an apple. But water will react with intermediate species. What do we need to do to get over here? I'm sorry, we're not making that. We're making this one, right? We got isopropyl carbon with an OH, and that's a CH3. We got a CH2 mercury. Obviously, we got to get rid of the mercury. What do we need to replace the mercury with to get this? The hydrogen. This is the hydrogen source. Hydride. It's H minus source. As an aside, let's look at the structure of that. It's a boron with 4 H's. Boron is minus, and then it's got a sodium. Okay? But this boron is like H, I like you, but you and your electrons take a hike. So the H and the 2 electrons, it's H minus. Boron kind of shoots these H minuses off. So it can go back to neutral. H minus source, we'll see that a lot more in organic 2. You can actually use it with me in organic 2 in the lab. There. How might that happen? I'm going to show you a mechanism, but it's probably not correct. I'm going to show you this way because it sort of matches what we've done before. We can say these electrons attack the carbon. And what do we need to do when we attack the carbon? Kick off the mercury. These electrons move on to mercury, and now we have 3 H's bonded to the carbon. and the mercury left. What's the charge of the mercury now? Because it's neutral bonded, but when this moves on to mercury as an extra long pair, there may be others. Now we count that as an extra electron because we count them both. So what's the charge of the mercury? Negative. That gives us our final product. Now I want to keep track of the mercury there. Connor?
So watch the OH go from up to down in that final product.
Just like this. Why did my thumb go forward to back? It's just rotated. There's no stereochemistry here given. There could be stereochemistry because if we showed these bonds, would we show both bold or one bold, one dash? Both bold, and if that's bold, how does the water attack? Okay? But in terms of what your question is just, I mean, I could draw it out. It doesn't matter. Okay, that's called an oxymercuration. We mercurated, but we also brought in the oxygen. Sarah?
What is the H minus one enzyme? Is there a reason why it's going to, or that just due to chemical?
It's a good question. The mercury, well, also I told you that's probably not the
Yeah,
mechanism.
so,
Probably not the mechanism. The mechanism is more probably convoluted. I just want to show you that to reinforce a potential way. Also, this does form, show you the final fate of this. Final fate of this is this acetate ionizes off and you get mercury plus acetate. So the acetate is minus, what's the charge of the mercury? There's a minus over there, there's a minus over here, so what's the charge of the mercury? Neutral, okay? Neutral mercury. That's mercury metal. That's metallic mercury. Okay, you put 0 up here. Okay, like in your thermometer. This reaction does form mercury metal, which today is not good, environmentally hazardous, sort of being phased out. That's one reason this reaction is really not great anymore, but it's a very classical textbook mechanism. Okay, called oxymercuration. If you use an alcohol instead of water, it would be called alkoxy. If the oxygen had an alkyl group on it, like an alcohol. You can make ethers this way. Okay, after that's new, but do you see the similarities in other mechanisms? What's the key intermediate? Mercuronium ion, water attacks, most substituted carbon. Isn't that sodium borohydride is the second step that gets rid of your mercury and replaces it with an H?
What else with the acetate hydroxide? That's just still there in solution.
With what?
The acetate hydroxide. No, it came from Cyclohexene.
That's not acetate hydroxide. That's acetic acid.
Acetic acid, sorry.
If we draw that out,
So is that just, that's still there in solution?
that's acetate with an H, it's acetic acid. Yeah, it's in solution. That acetate's in solution. This mercury probably separates as mercury globules. Okay. Now that is called standard Markovnikov product, where the OH ends up on the more substituted carbon. Because that's where we would expect it. So let me ask you this. Why do we not expect the OH to be on the end carbon? Why do we not expect the OH to be here? Because when we attack these three-membered rings like this, we attack the more substituted carbon. And the OH ends up on the more substituted carbon. That's called Markovnikov product. All right? And that's something that you can't forget. All right? I'm not interested in that. I'm interested in you knowing mechanistically what the outcome is. Somebody may say, show me the Markovnikov product. complete ignorance. Tell them, just show me the reaction. I'll show you the product. I don't know what microbial company is, but I'll show you the product. Tell them that. Okay? All right? And they may ask you, well, doesn't that end up on the most substituted carbon? Well, I would look at your product and say, well, it does. I reckon it does. No mechanism. Don't know all these little trick things. All right. Well, how can we get the OH over here? We know how we can get the OH over there, a rearrangement. And it rearranges with just proton in water. Mercury in water, it doesn't. Why does it not rearrange? Because there's no cation formed, right? That's not actually formed. No cation here to rearrange. Well, how do we get OH on the least substituted carbon? By the way, that would be a non-Markovnikov. How do we get non-Markovnikov outcome? The reaction below. By the way, what type of products are we making here? Alkene to alcohol. Oxymercuration gives an alcohol. Ultimately, what are we adding to the alkene when we do this process? What are we adding to this? What's the difference in formula between this and this? We're adding water, right? What are we adding when we do this? We're adding water. In terms of formula. Those are both hydration reactions, but one is primary rearrangement, the other one's not. A third hydration reaction is down here, hydroboration oxidation. These reagents ultimately add water to the formula, and you get an alcohol, but they give non-Markovnikov. And if we look over here, it's our last one as we make the loop around. The last one in the middle there. We also have boron again. And the first step is to react the alkene with BH3. BH3 is called borane.
Would BH3 be relatively non-polar? It says that
BH3 is what hybridization? Is there a lone pair? Where's boron on the period 2?
4 carbon.
I mean, what group? Group 3. It's only got 3 valence electrons. It's using the 3 here. Boron does not have an octet. Here's your BH3. Hybridization is sp2 with a what? MTP orbital. Since it has an MTP orbital, is it going to be electrophilic or nucleophilic? Like electrons. Give me some electrons.